Okay, like I said, if there are any questions that you might have, please feel free to interrupt me. Just give me a shout out. Huwag kayong umasa na makita ko yung chat question nyo. I will probably see it, but I might see it too late. So let me share my screen. Okay, I hope everybody can see my screen okay. No? So let me just recap what we discussed about drift. So let me recap our discussion on drift. No? When does drift occur? Drift occurs when there is an electric field in the presence of charge carriers. No? When charge carriers are in the presence of an electric field. That is when drift occurs. So if I have an electric field, for example, in this direction, and I have an electron, what direction of force will my electron feel? Anyone? What direction of force will my electron feel? Will it be to the left or will it be to the right?
To the right. To the right.
Yes. No? So I'm going to get a force. I'm going to get a force in this direction. Now, normally, that force will cause my electron to accelerate. No? So that will cause my electron to accelerate. Normally causes acceleration. But why will my electron not accelerate? Can somebody answer me? Why will my electron not accelerate? We're talking about if it is in a semiconductor. Anybody remember?
Because of scattering.
Yes, that's right. Exactly. No, thank you for answering. No, because of scattering, the electron will not accelerate. No, as a matter of fact, you might see the electron go this way. No, it will go that way, that way, that way, that way, that way, and so forth. But there will be a net velocity or an average velocity in the direction of my force. There will be an average velocity. Okay? Now that average velocity will be proportional to the electric field intensity. So V n, so this is your average velocity of your electron due to drift, okay, is proportional to your electric field intensity, and the constant of proportionality is mu of n. What is mu of n? This is mobility. Mobility of electrons. No? Mu of n is your mobility of electrons. No? Okay, you also have drift due to holes, and this is going to be mu of p e, no? Where mu of p is your mobility of holes. Okay. electrons move opposite the direction of your electric field. No? Opposite the direction of your electric field, but electrons has a negative charge. No? So because it has a negative charge, it looks like, from the point of view of charge displacement, it looks like positive charges moving in the same direction as your electric field. Okay. On the other hand, holes will move in the same direction as your electric field. So actually, uh, um, from the point of view of current, electrons and holes contribute to current in an additive manner from the point of view of current. Again, no, let me explain that again. Electrons move opposite the direction of the electric field, but because electrons have a negative charge, it looks like positive charge is flowing in the same direction as your electric field. On the other hand, holes move in the same direction as your electric field. So from the point of view of current, they contribute to each other. Okay. What did we say about the mobility of electrons? Mu of n is approximately equal to 3 times mu of p. That electrons have 3 times the mobility of holes. No? In other words, mas maliksi yung mga electrons natin kaysa yung mga holes. No? In an intrinsic semiconductor, in intrinsic silicon, no, mu of n is equal to ano ba yung value ng mu of n? Sorry, 1,400 if I'm not mistaken, no? No, sorry, 1,350. Okay? This is centimeter squared per volt second. And mu of p is 480 centimeter squared per volt second. So yun yung mu of n at saka mu of p. Again, no? So the key takeaway here is in the presence of an electric field, you do not have acceleration. No? Because of scattering, you will approach an average velocity. That average velocity are given by these two equations. For electrons, mu of n e. For holes, mu of p e. No? And then these are the typical values of mu of n and mu of p for intrinsic silicon. Okay. Now what we're interested in is current density. Current density. Okay. Current density is amperes per centimeter squared. We showed you last time that for holes, Jp, this is the current density due to holes, due to drift. The drift current density due to holes, okay, is equal to Q, okay, P, mu of P times electric field intensity. No? Where Q is equal to charge, which in this particular case is equal to E, or 1.602 times 10 to the minus 19 coulombs. No? Because that is the charge of one hole. No? P is your hole concentration. No? In the same manner, we said that J's of n due to drift, or the drift current due to electrons is Q n mu of n E. No? Your total drift current density, no, that is J drift, is equal to Jn drift plus Jp drift, which is now going to be equal to E. So Q is equal to E n mu of n plus P mu of P multiplied by electric field, the magnitude of your electric field intensity. Again, I explained last time why we use this symbol for electric field intensity. Where this quantity here, we call this sigma, or we call this your conductivity. Right? What are the units for conductivity? This is Siemens per centimeter. No? So we try to use centimeter as our standard unit of measure here, in this particular module. Siemens per centimeter. And the reciprocal of conductivity, we call rho. This is now your resistivity. Resistivity, no? Which is in ohms centimeter. And somewhere, maybe in the past, maybe high school or maybe in physics, you learned that you can compute your resistance, no, by multiplying resistivity by length over cross-sectional area. This is resistance. No? Where you can see that your resistance increases as your length increases, and your resistance decreases as your area increases, which makes sense. If you have a large area, mas madaming pwedeng daanan ng charge carriers, so you have a smaller resistance to current flow. If you have a small area, mas ipit yung charge carrier, so you have a larger resistance to current flow. So this is your formula for resistance. Okay. Having done that, we can go to an example. What is the resistance of a silicon rod at room temperature if it is 1 centimeter long and has a cross-sectional area of 0.25 centimeters squared? The sample is doped with 10 to the 16 donor atoms per centimeter cubed and 5 times 5 times 10 to the 15 acceptor atoms per centimeter cubed. Now, we assume that at these doping levels, given itong values ng mobility. So these values of mobility are given. So let me ask you, what type of semiconductor is this? Is this an N-type or is it a P-type? May I hear someone shout out an answer?
Sir, is it at N-type?
N-type po.
That's right. No, thank you very much for answering. It is an N-type. No. My next question: what is approximately the value of N going to be? What is the value of N going to be approximately? Actually, ginawa natin ito nung Tuesday. No, these are exactly the same concentrations I gave. What is the value of N going to be?
Is it ND minus NA po?
Yes, that's right. No, N is approximately going to be ND minus NA. No, which is your net donor concentration. No? Remember what I said last Tuesday? If ND is equal to NA, and both ND and NA are your typical doping levels, ano? If ND is equal to NA, what does the semiconductor look like? What does it look like? Is it an N-type or is it a P-type? If ND is equal to NA.
Intrinsic.
Yes, exactly. It looks like an intrinsic. Kasi for every donor atom you have an acceptor atom. So, pupunta lang yung mga donor atoms mo dun sa mga acceptor atoms natin, no? So, in effect, wala kang additional charge carriers. So, when ND is equal to NA, it's intrinsic. So, how do you make it N-type? ND has to be greater than NA. How do you make it P-type? NA has to be greater than ND. This is assuming that you're starting out with an extrinsic semiconductor. If you're starting out with an extrinsic semiconductor, if it is N-type, you can convert it to a P-type. If it is P-type, you can convert it to an N-type by just adding impurities that will neutralize the initial impurities plus some more. So this is your net donor concentration. But we actually solved this already last time. when we solved this last time, we got N is going to be equal to 4.5 times 10 to the 15, no? Kasi 10 to the 16 minus 5.5 times 10 to the 15 is 4.5 times 10 to the 15. This is electrons per centimeter cubed. And P, ano nga ba yung value ng P na nakuha natin dito? Trying to look for it, no? We saw this last time, no? The value of P was yeah, 50,000. And we got P equal to 50,000. This is joules per centimeter cube. So actually, kung alam natin yung N, alam natin yung P, ang dali natin kunin yung conductivity. So what is this? This is just E N use of N plus P use of P, no? So fill in the values na lang. What is this? 1.602 times 10 to the 19. That is E, no? 4.5 times 10 to the 15 times use of N, which is anong use of N? Times 1,100. By the way, no? Just make sure that your units are consistent, no? In other words, you don't have to worry basta't alam nyo consistent yung units nyo, no? If your units are not consistent, you have to make them consistent. So times 1,100 plus 50,000, no, times 400. No? So yun lang yun, no? 50,000 times 400. No? And I'm going to get 0.793 Siemens per centimeter. So what is now my resistivity? It's going to be 1 over sigma, and I'm going to get 1.26 ohm centimeter. So finally, what will be my resistance? R rho L over A. So this is 1.26. L is 1 centimeter long. A is 0.25. I'm going to get 5.04 ohms. Yun ang magiging resistance nitong 1 centimeter long, 0.25 centimeter squared silicon rod. Just for comparison purposes, no? For comparison purposes. Your intrinsic silicon of the same dimension will have R equal to 909 kilo ohms. You can solve this. No? If this is intrinsic silicon, anong value ng N at saka P? Kung intrinsic silicon, anong value ng N at saka anong value ng P? Anyone? At room temperature. Anyone?
Yung Ni value po ba?
Exactly, Ni. No? If this is intrinsic silicon, N is equal to P is equal to Ni. So you can feed that into this equation. No? This becomes Ni and this becomes Ni. No? And then you multiply that by use of M, use of P, and so forth. And then you multiply it by L over A. Ito yung makukuha yung resistance. Compare this resistance to this resistance. No? 909K versus 5.04 ohms. So obvious that this will conduct current much, much better than this. 909K, laki niyan. It's almost 1 meg. No? Samantalang ito, ang liit nito. No? So, by just doping it at this particular doping level, which does not change its chemical properties, we were able to reduce the resistance by a factor of 20,000, I think, or something like that. No? Anyway, no, you can compute. 909,000 divided by 5. Any question with regard to this example? Any question? Very straightforward, diba? So if you're given the doping level, and you know the mobilities, you should be able to determine the conductivity, and you should be able to determine the resistivity. If you know the dimensions, you should be able to determine the resistance. And if you know the resistance and you're given a voltage, you should be able to determine how much current is flowing using Ohm's law. So simple as that. I want you to do this seat work. No? Let's take 10 minutes. Actually, in my other class, most of the people that answered got it in about 5 minutes. No? So uh this is just review of what we just took up just now. No? So let's take 10 minutes here, do this seat work. And if you have an answer, please post it. No? And then I'll tell you whether your answer is right or wrong. Okay, I have quite a number of correct answers. Thank you. There are some wrong answers, but thank you just the same, ano, for trying to solve the problem. Give you one more minute, no? Okay, so let's try to do this together, no, for the sake of those that weren't able to solve the problem. Okay, so we know the resistivity. What is your resistivity? Rho, sorry. Rho is equal to 1 ohm centimeter, and therefore sigma is 1 Siemen per centimeter. Rho is just equal to the reciprocal, sigma is just equal to the reciprocal of rho. Now, what is sigma? We know that sigma is equal to E, Q is equal to E in this case, N, use of N, plus P, use of P. No? Very simple formula. So let's just feed in what we know. No? So sigma is equal to 1. Again, no? Make sure your units are consistent. If it's centimeters, make sure everything is centimeters. What is E? 1.602 times 10 to the minus 19. No? That's coulombs. If you use 1.6, that's okay. No? 1.6 is an acceptable approximation. Okay. What is N? Well, we don't know N. Ano? We don't know N. Muse of N is 1,350. We also don't know P. Muse of P is 480. But we know that P is equal to Ni squared over N. Right? So let's uh, compute, no, intermediate values. So this is 1. Okay. 1.602 times 10 to the minus 19 multiplied by 1,350. This is going to give me 2.1627 times 10 to the minus 16 times 10 to the minus 16 times n. Okay. On the other hand, 1.602 times 10 to the minus 19 times 480 times ni squared will give me 17,301.6. And now this is divided by n, no? Because that's ni squared divided by n. No? So that ni squared has already been multiplied by 480 and by 1.602 times 10 to the minus 19. So you only have one unknown. No? N. So you can solve for n. And this is a quadratic equation. If I solve for n, what am I going to get? I'm going to get n is 4.6238 times 10 to the 15. Actually, dito, you can already state, ano? You can already state as an approximation the net donor impurity concentration is going to be equal to N, no? So this is approximately equal to the net donor impurity concentration. But if you want to be exact in your calculation, what formula will you use? Anyone? What formula will we use? Kung gusto nating exact calculation. No? You use neutrality. N plus Na is equal to P plus Nd. No? And your net donor concentration, which is equal to Nd minus Na, okay, is going to be equal to N minus P, or 4.6238 times 10 to the 15 minus, ano ba yung value ng P? Di ko pa pala nakukompute yung value ng P, no? P is going to be equal to Ni squared over N. Let me compute for that, no? P is equal to 48661. Okay? So ito yun, no? Ni squared over N. Kapag kinalculator nyo to, baka hindi niya makita tong 48661, ano? So this is going to be approximately equal to 4.6238 times 10 to the 15. Yun din yung lalabas sa calculator niya if you do this calculation. So you know that the difference between Nd and Na must be equal to this. Now, if Na is equal to 0, for example, if this was a pure N-type, no, walang acceptor concentration, then we know that Nd will be equal to this particular value. Any questions with this example or with this sheet work? Again, thank you very much to all of those that tried to solve the problem. Questions? Let's put the units to be complete, ano? So this is donors per centimeter cube. No? Oops. Can you still see my screen okay? Okay pa ba? Okay. Let me restart my my presentation. Okay, that's better. There was something wrong earlier. Okay, so let's go to the next topic, diffusion. So we said that there are three mechanisms for carrier flow in a semiconductor. First is drift, second is diffusion, the third is electron hole pair generation and recombination. Okay. What is diffusion? Diffusion is the tendency of carriers to spread themselves out uniformly over a given volume. The tendency of carriers to spread itself out uniformly over a given volume. So this occurs when charge distribution is not uniform. And diffusion is a natural phenomena. It is a natural phenomena. Let me ask you this. what will happen if I have a glass of water and I drop one drop of black ink? What do you think will happen, no? Or what will you observe? Can somebody give me an answer? Anong mangyayari?
Magiging slightly blacker yung buong water.
Chika, tapos si Bon nag-away?
Ano yan? Ano yun? Sorry. John, can you repeat?
Magiging slightly blacker yung ink po.
Okay. That's correct, ano? But eventually, will the water be of an even color, or will it be black in some spots and light in some spots?
It will be even.
Yeah, eventually it will be even, no? Actually, if it's just one drop in a glass of water, you may not even notice that it is actually darker, right? But tama yung sinasabi ni John na eventually all of the molecules, black ink molecules, will spread itself out evenly in the glass of water. That is diffusion. No? It's a natural phenomenon. It is a statistical phenomenon, actually. It's a statistical phenomenon or a natural phenomenon. And the same principle applies with semiconductors. So let me present to you this scenario. No? So this is a semiconductor. Let's assume it is intrinsic, neither n-type nor p-type. Let's say we inject holes continuously. No? So this is a continuous injection. No? Let's say continuously injected. What is going to happen? When you inject holes here, there's going to be a very large concentration of holes where it is injected. And that will cause your holes to diffuse toward the right. But as you're going to the right, that concentration will decrease. No? So here you'll have heavy concentration. Here the concentration will be less. Here the concentration will be less. So increasingly decreasing. No? Okay? So eventually you're going to have this concentration profile. This is what diffusion will dictate. No? Okay, you're going to have that concentration profile. Where are our holes moving? Our holes are moving in the x direction. No? Therefore, we will have hole diffusion toward the right. And because current flows in the same direction as hole movement, you have hole current flowing toward the right. No? That is what will happen in this particular scenario. No? So we're not going to discuss anymore how I know that this is going to be exponential, but this is what will happen actually. No? It will be an exponential distribution. The magnitude of diffusion current is proportional to the rate of change of carrier concentration. No? So the magnitude of diffusion current is proportional to dpdx. What is dpdx? dpdx is the slope of this curve at any given point x. At any given point x, dpdx is the slope at that particular point. Notice that dpdx is going to be negative. dpdx is going to be negative. Why? Because our function is a decreasing function. So our slope is going to be negative. But the direction of current is in the direction of x. So this is negative. The direction of current is in the direction of x. So we have to put a negative sign here. That's the reason for this negative sign. Okay? And then what is the proportionality constant? It is going to be Q multiplied by a constant which we call the diffusion constant. So again, current density due to diffusion is going to be minus Q multiplied by your diffusion constant multiplied by your slope. So I explained to you why it is negative. No? Because this is negative, So you have to put a negative sign here so that the direction of current flow is in the positive x direction. Now, similarly for electrons, this is your formula. Okay? Bakit nawala yung negative sign? Nawala yung negative sign because, okay, this is going to be decreasing. So our electrons are going to be flowing toward the right, but the current is going to be flowing toward the left this time because current is opposite the flow of electrons. No? So this is negative. When you compute this whole thing, it will be negative. It will give you the correct sign. Negative meaning to say it is in the opposite x direction. So this is your expression for hole diffusion current, and this is your expression for electron diffusion current. So dP, no, sorry, this is supposed to be dN. No, let me correct that now. I cannot correct it. Sorry. Let me just annotate it. No. This is supposed to be dN. dN. No? So dP and dN, that would be somewhat related to mobility intuitively. I mean, if the carrier is more mobile, then the diffusion constant should also be greater. No, if the carrier is less mobile, then the diffusion constant should be smaller, and that is illustrated here. No, dP is 12 centimeters squared per second. dN is 35 centimeters squared per second. Notice that dN is almost 3 times the value of dP. If you remember mobility, the mobility of electrons is almost 3 times the mobility of your holes. Okay, so let's take this example. I'm not going to make you solve this. No, let's do this together. The electron concentration profile shown has been established in a piece of silicon. So this is the electron concentration profile. Now this is purely hypothetical. I don't know whether we can really establish such a concentration profile. But this is the electron concentration profile. Let's assume it is linear. Okay. Given the value of n's of O, that is the concentration at x equal to 0, and given the value of W, no, that is the base of the triangle, determine the electron current density along the x-axis due to diffusion. So what is the current density along the x-axis due to diffusion? Okay, so let's do this together. What is the slope? What is dN dx? Okay. dN dx is equal to n's of O over W. Okay? Question. Tama ba to? 10 to the 17 over 1? Tama ba yan? Anyone?
No po.
Bakit?
Yung unit po ng W is in micrometers po.
Exactly, no? So, ang one micrometer is actually 10 to the minus 4 centimeters. No? So this is 10 to the minus 4 centimeters. So we have to be consistent in our units. So if this is 10 to the 17, in this particular case, electrons per centimeter cubed, the W should be 10 to the minus 4 centimeters. Okay. May isa pang mali. Ano pa yung mali?
Yung sign po.
Yes,
Dapat
this should
po
be
negative.
negative. No? Sorry. Nasaan ako? This should be negative. Right? Why? Our slope is negative, no? Instead of increasing, decreasing. In other words, ang delta y natin is negative, no? So it's what is our this is 0 minus NO over W minus 0, no? It is negative. Okay? Okay? So this is the NDX, no? So just apply the formula now, no? What is N due to diffusion? This is E dN by dx. No? So simple 1.602 times 10 to the minus 19. By the way, whenever we plug in the value of E, this is the absolute value, no? Because it is just the magnitude of electric charge. Just because I put there E doesn't mean it's negative 1.602 times 10 to the minus 19. No? Multiply this by 35, and then multiply this by 10 to the 17 divided by 10 to the minus 4. This is minus 10 to the 21. No? 21. Okay. What am I going to get? I'm going to get minus 5.607 amperes per centimeter squared. 5.607 amperes per centimeter squared. What is the direction of current? Since this is negative, so current is in the negative x direction. Negative x direction. No? In other words, it is right to left. Any questions? Okay. So ito na yung solution. No? Okay. Remember what I pointed out earlier? No? Ito yung magiging concentration profile if you have this particular scenario. Okay. But think about it, ano? Yung slope nito nagpapalit, hindi constant yung slope. The slope of this is changing. The slope is becoming smaller and smaller as x becomes larger. And your current is proportional to your slope. So what does that imply? That implies that as we go toward the right, our current due to diffusion is changing. If we have this particular scenario, our current due to diffusion is changing. Question is this, no? Can the current here be different from the current here, be different from the current here, be different from the current here? That defies Kirchhoff's current law. Ang sabi ng Kirchhoff's current law, kung meron kang current na dumadaan dito, dapat pare-pareho yung current na yan. No? Hindi pwedeng dito, iba yung current dito, iba yung current dito, iba yung current dyan. Iisa lang dapat yung current dyan. And yet, this is your concentration profile due to diffusion. No? I just wanted to point this out. No? Ang ibig lang sabihin nito that in this particular case, diffusion is not going to be your only source of current. There will be other current components. And those other current components are going to make your current uniform throughout your current path. Any question with regard to that? Any question? Okay, so you can compute, for example, for your diffusion current here, no? But that diffusion current will not be your only current. Okay. So obviously there's a relationship between diffusion constant and mobility. And that relationship is called Einstein's relationship. The ratio of diffusion constant to mobility is equal to a constant. and that constant is equal to your thermal voltage. Your thermal voltage. The formula for thermal voltage is kT over Q, where K is Boltzmann's constant and Q is the magnitude of electron charge. This is Boltzmann's constant. If this is Boltzmann's constant, anong value ng Q na dapat kong gamitin? Anyone? No? If this is Boltzmann's constant, what value of Q should I use? Is it 1.602 times 10 to the minus 19? Yes or no? Anyone?
No po.
Why? Why no?
Because yung electron po is, may electron volt po na unit sa constant. So,
Thank you very
mag-cancel out.
much, Mr. Franny. No? Kasi ito given in electron volt eh. No? And therefore, yung Q should actually be equal to 1 electron because that's the magnitude of your electron charge. No? If this is given in electron volts, then Q should be in terms of the number of electrons. And in this particular case, Q is 1 electron. Okay, so numerically, K over Q numerically is 8.62 times 10 to the minus 5. That is K over Q, no? 8.62 times 10 to the minus 5. Okay, if you multiply 8.62 times 10 to the minus 5, if you multiply that by 300 degrees Kelvin, which is room temperature, you're going to get V of T is approximately equal to 26 millivolts. So, tandaan nyo tong numerong to, no? 26 millivolts. Kasi when we say room temperature, and you need to know what is the thermal voltage, usually we will accept, no? 26 millivolts tatanggapin namin yan. Okay? If you're given another temperature, no? Sabihin natin, no? They ask you what is the thermal voltage at let's say 200 degrees Kelvin, wala kang choice, no? You're going to have to use this. Another way of determining VT, another alternative formula is VT is equal to T over 11,600. Subukan nyo, no? 300 divided by 8.62 times 10 to the minus 5, that should give you about 0.026. That's T over 11,600. Any questions? Okay, so in summary, we want the total current density. If we want the total current density, then we have to add the current density due to electrons and the current density due to holes. Each of these, Jn and Jp, will consist of a component due to drift and a component due to diffusion. So for electrons, your component due to drift is Q and mu of n E, where Q is actually equal to E. No? But let's put Q para ang ilagay nyo is 1.602 times 10 to the minus 19. No? Hindi yan 1E. No? So Q is actually 1.602 times 10 to the minus 19. No? And then this is your current density of electrons due to diffusion. No? Ito naman yung current density of holes due to drift. Ito naman yung current density of holes due to diffusion. So take note, for electrons, they are additive. For holes, they are subtractive. They are subtractive, no, for holes. Okay? So I'm going to go to the last mechanism for carrier flow. Okay? This is recombination and generation and recombination. We're talking here about generation and recombination of electron hole pairs. So generation is when an electron hole pair is created. Recombination is when an electron recombines with a hole and eventually becomes a whole covalent bond, which is which is neutral. No? So the word that was used here was annihilated. Kasi nag-disappear both yung electron at saka yung hole. These processes act to change carrier concentrations. No? Although in thermal equilibrium, they cancel each other out. No? But they tend to change carrier concentrations and therefore indirectly will affect current flow. So this is going to be very short. This is going to be very qualitative or very descriptive. Let's start with generation. There are three common mechanisms for generation. The first is what we call band-to-band generation. Okay. So initially, this was a covalent bond containing an electron. So initially, covalent bond yan, containing an electron. It receives thermal energy or energy in the form of light. What happens? No? The thermal energy or energy in the form of light will elevate the energy state, the energy level of this, and enable it to cross the forbidden band and to go into the conduction band, thereby leaving a hole. And you call this band-to-band regeneration. No? The thermal energy or the light energy imparted on the valence electron will be enough to make it cross the band gap. So yun ang tawag na band-to-band. Kaya tinawag na band-to-band. In silicon, this is not the usual case. In silicon, there are what we call energy traps. What are these energy traps? These energy traps are energy states that exist in the forbidden band that are created by either impurities or by imperfections in the lattice structure. Again, energy traps are energy states that are created in the forbidden band that is due to impurities or due to imperfections in the crystal structure. So we do not expect, for example, a silicon to be, let's say, 100% pure. No? At the most, you can only make it 99 point maybe 99999% pure, but there's still that 0.00001 possibility that there will be one impurity. Okay. Now that impurity will introduce an energy state or could introduce an energy state that is actually in the forbidden band. No? In the same way, you remember dopants. Dopants introduce energy states. Yung donor impurity introduces an energy state right below EC. Acceptor impurity introduces an energy state right above EV. Well, an impurity will introduce an energy state. We call it E of T or an energy trap. No? Now, what does that allow us to do? It allows this electron in this valence band to go to the conduction band in installment, hindi yung diretso. No? The thermal energy or the light energy may not have been enough. So ang unang pupuntahan nito is an energy state in this particular energy trap. And then receiving additional energy, saka pa lang siya pupunta sa conduction band. No? So we call this trap-assisted generator. So dalawang installment to, no? Imbis na one give, two gives. Okay. Any question with regard to that? The third possible mechanism for generation process is what we call impact ionization. Impact ionization. And this happens this will happen in semiconductors under the influence of large electric fields. No? Later on, you're going to find out that this will happen in a diode in the vicinity of the junction where there is a very large electric field. You call it impact ionization. What happens? No? What happens in impact ionization? Okay, so we have an electron here that's already in the conduction band. By the way, because you have an electric field, and we're going to study that later on. Your energy band diagram is not going to be horizontal. It's going to have a tilt. No? In this particular case, if your electric field is right to left, your energy band diagram is going to tilt downward. Tilt downward. Okay? Don't worry, no? We're going to explain that in the next lecture, why there is this tilting of the energy band diagram. But okay, so let's start with an electron. An electron experiencing this large electric field. So its initial tendency will be to accelerate. Of course, we mentioned earlier that eventually, because of scattering, it will reach a drift velocity. But its initial tendency will be to accelerate opposite the direction of the electric field. It might have accelerated enough to collide with an electron in the valence bond. Remember, this is not physical location. These are energy states. No? So the location of this electron in this valence bond can be the same as the location of this, no? Or in proximity to the location of this electron. So this might accelerate enough to collide with an electron in this valence bond. So what will happen? No? This electron will now be promoted to the conduction band, and the energy of this particular electron will now go down because of that collision. So it will still be in the conduction band, pero babagsak siya. No? It will go down. So the energy of this will go down. On the other hand, this will be promoted here. So that's what you call impact ionization. And sometimes, no, sometimes that creates a chain reaction. And later on, you're going to see that that's actually what happens in a Zener diode. No? If you know what a Zener diode is, no? That's what happens when a junction breaks down. Okay, but we'll get into that. We'll get into that more later on. So this is the only thing you have to understand about impact ionization. Again, no, to summarize, this will tend to accelerate. It will hit a valence electron. That electron will be promoted to the conduction band, and the energy of this will drop down because of the collision. That is impact ionization. Any question? Let's talk about recombination. So the first two cases are just the opposite of the generation cases, no? Or just the inverse of the generation cases. So the first mechanism is what we call direct recombination. So this is an electron. It sees a hole. Okay, an electron, it sees a hole. Again, remember, this is not physical location. This electron and this hole can see each other or can end up being in the same location. No? So what will happen? This will now occupy the hole and will make a neutral covalent bond. No? So this X is a neutral covalent bond. Okay? But this would have had to drop energy. So that energy will go somewhere. No? Where will it go? It will either be in the form of heat. No? So this, when it recombines with this, will release energy. It will either be in the form of heat, or it can be in the form of light, which is actually how an LED works. How does an LED work? You have this electron, no, recombining with a hole, and then the energy that it loses, okay, corresponds to a certain wavelength that it will emit in the form of light. That is the principle of your LED. Okay, you can also have recombination through this recombination centers or through these traps which we earlier described. And there are two ways. One is electron here loses energy, no, it goes down to this energy state, and a hole here goes up to this energy state, no, and then they recombine at this energy state, forming a covalence bond, no, in the impurity atom, for example. No? Okay, so that's one way, no. So nandito yung final covalent bond. The other way is yung parang two gives kanina. No? So we start with this electron, it loses energy, it goes down to this energy trap, and then it loses energy again and recombines with a hole, thereby forming now a full covalent bond. No? So that is recombination through recombination generation centers. And in this particular case, either this mechanism or this mechanism, the energy lost is in the form of heat. The third mechanism, which we call Auger recombination, this is prevalent in very highly doped material. What happens? This electron loses energy, recombines with a hole, and this becomes a hole covalent bond. Saan pupunta yung energy nitong electron na to? It is transferred to another electron. No? So yung energy niya na na-release will be absorbed by another electron, which is already in the conduction band. Again, no, this will lose energy, recombine with the hole, form a covalent bond. The energy released by this will transfer to another electron, which happens to already be in the conduction band. No? So what will happen? This will go to a higher energy level. But because we said that electrons tend to sink, electrons tend to seek a state of lower energy, little by little, by nature, the energy of this electron, no, the elevated energy of that electron will slowly go back toward E sub C. And you call that Auger recombination. And that's it. No, that's the completion of topic 1, part 2, or the completion of topic 1 of this course. We only have 15 minutes left. If we had more time, actually, dun din sa isang klase ko, we didn't have more time. If we had at least 10 more minutes, I would have started with the topic 2 already. No? But because we only have 15 minutes left, I will forgo that. No, I'm going to just dedicate the rest of the time, just in case you have any questions. So, are there any questions? Any questions?
Sir, for trap assisted po na generation, is it tawag yun? Can that be considered like another band po?
Yes. No. Not another band. An energy level.
Energy level.
A discrete energy level. Kasi yung mga itong energy level na to, that is made up of impurities na madalang dun sa silicon, no? Yung sinasabi ko kanina, hindi naman pwede talagang 100%, absolutely 100% na walang impurity, no? There might be an impurity na madalang. Okay? So if you find that particular impurity, this will only be one energy level, no? It will not be bands. Bands will be when you have many such impurities which interact with each other. So this is just one energy level. And it will fall in the forbidden band. It will fall within the band gap. So yun yung reason why pwedeng 2 gives yung promotion nito to the conduction band, no? Una, pupunta muna siya dito sa energy level because it is available. and then subsequently go to the conduction band. Did I manage to answer your question?
Yes po. Thank you po, sir.
Any other question? Okay, I have an important announcement. And I told you this at the start of the semester. There's a very strong possibility, in fact, almost certain, that I will not be able to meet you next week. No? I will tell you for sure by Saturday, no? But um, almost certain, like I said, I will not be able to meet you next week. Okay. What am I going to do? I'm going to point you to some old lectures that I conducted during the pandemic, just to introduce you to uh, topic 2, basically. No, but we're going to go through it again. But I would highly recommend that you at least go through those old lectures. No, yes, no, Tuesday and Thursday next week. That you go through those old lectures so that I can go at a faster pace. Okay, kasi kailangan maghabol tayo ng konti. Although I don't see it as too much of a problem kasi may buffer na pinrovide ang triple EI, may buffer for the first exam, I think 1 or 2 meetings. So I think makakahabol naman tayo, mawawala lang yung buffer natin for review, no? And then I might post an exercise in UVLE that I will require you to do, no? Depending on how much time I have, sorry, but I'm going to be quite busy the rest of the week. So but yun, I will try to post an exercise. So please watch out for those announcements. Okay? If nobody has teka, may tanong ba sa chat? Yeah. If nobody has any more questions, then that's it for this session. As is my practice, I will only turn off the session when all of you have signed off, no? Just in case any of you may want to still ask me any question. So that's it, and thank you, no? So may possibility week after next na tayo uli magkita.
Thank you po, sir.
Yeah, you're
Thank you po,
welcome.
sir.
Thank you po,
Yes.
sir.
Thank you
Thank
po,
you
sir.
po.